Welcome to Higher Structure Seminar Series. Today our speaker is Juan Orendain from Case Western Reserve University. Actually, Juan also spoke in the very first year of our seminar series, so he we thank him again. And today he will tell us about cross products of decorated bicategories. Please, Juan.
Well, thank you very much, Alan. It's a pleasure to be back in the seminar. It is a great seminar, and I enjoy watching the talks online, mostly on YouTube. But it is an amazing seminar. So congratulations to you, and I'm honored to be part of it. All right. So as Ilhan mentioned, the title of the talk is Cross Products of Decorated by Categories. So in this talk, I will tell you a story about a conjecture on this invariant that I call the length or the vertical length of a double category, and the conjecture is on a computation of the length on frame by categories or equipment. So I plan on spending half of the talk on background material, and then the second half of the talk I'll spend it talking about the techniques that I will use to solve this conjecture in a special case. So the plan is the following. So I'll start with globularly generated double categories, a brief introduction to double categories and bicategories, and then I'll talk about globularly generated double categories. Then I'll talk about the length invariant and about equipments. And then I'll spend the second part of the talk, so parts 3 and 4, talking about Pi2 indexings and this cross product operation. And then on part 4, I will try to explain how to use this to prove this conjecture that I mentioned for fully faithful and absolutely dense equipments. So I will assume throughout that the audience has some familiarity with bicategories, maybe some, though not much, familiarity with double categories, and then probably that you've heard the word equipment or frame by category. But if you haven't, and you want to interrupt for me to define something or say something else, just please unmute yourself and do that. I'd be very happy to hear questions. All right, so we'll start with globularly generated double categories. So in the zoo of two-dimensional categorical structures, one usually works with either bicategories or double categories. So bicategories are categories enriched over categories, functors, and natural transformations. These are, so I would argue, the most common two-dimensional categorical structure. If you're in the game of doing bicategories, then you're doing equations on pasting diagrams of two cells. The shapes of these two cells are usually either simplexes or globes. So if you're familiar with bicategories, this is sort of like the game you play. Now, double categories, on the other hand, are not categories enriched over categories, but are categories internal to categories, functors, and natural transformations. So these are also somewhat common, a little bit less so, but now being more studied this past few years. Um, in double categories, you don't consider pasting diagrams per se. You consider a very particular style of pasting diagram. You consider subdivisions of squares. And the shapes of two cells are squares as opposed to globes or simplexes in bicategories. So this, I would argue, are the two more common two-dimensional categorical structures. There's sort of two sides of the same spectrum of categorification. So on the one hand, you have enrichment, and in the other, you would have internalization. Now, in between these two structures, we have frame by categories or equipments. Now, frame by categories or equipments are double categories with satisfying an extra condition, or you can also think about them, if you think about them as equipments, as two categories with some extra structure, the equipment on the two category. These are also pretty common, but yeah, a lot less so than double categories and bicategories. The shapes of frame by categories, I will introduce them with a little bit more detail a little bit later, are squares, but squares that can be determined by a particular set of squares and globes. So the shapes of the squares, you could argue, are in between squares and globes. Okay. So the goal of this is that there are very well-established relations between the three types of structures. These are structures that are very well studied. But I argue that there is a deeper understanding of these relations to be had. And so I want to explore that. Okay. So before doing anything, let's just fix some notation. So in a double category, so a double category has a category of objects and a category of morphisms. So it has objects, vertical morphisms or vertical edges, horizontal morphisms, and two cells, which are squares. So in a double category C, uh, a two cell will look like this. It will be a square phi. It will have a vertical domain alpha, a vertical domain beta, a left frame F and a right frame G. And so these will have objects, which will be the vertices A, B, C, and D of the square. So I'll usually read squares from top to bottom. So here again, the vertical domain of phi will be alpha and the vertical codomain will be beta. And from left to right, so the left frame will be F and the right frame will be G. Um, so we will represent, or I represent usually one-dimensional identity. So sorry, before that, you can compose these squares horizontally and vertically, and you have an Ekman-Hilton argument for these compositions and all of that. Now, obviously, you would have horizontal and vertical identity uh, squares or two cells, but you also have one-dimensional identity. So we will represent one-dimensional identities as red edges, and so very important squares that we'll consider are horizontal identities. So for every morphism, for every vertical edge, F will have a horizontal identity square. And if that square will be of this form. So it will be a square having F as its left and right edge or frame, and it will have an identity as its vertical domain and its vertical codomain. We'll consider another very important class of squares, which will be the red boundary squares. So these will be squares such that all its boundary edges are identities, and so all the vertices will be the same. So if C is the double category and A is the common edge on these squares, we'll write pi 2 C comma A for the set of all these squares. So this is by the Ekman-Hilton argument, commutative monoid, where the operation between these is either horizontal composition or vertical composition. Um, we also consider globular squares. So globular squares are the squares of the shape that I have here. So these are the squares that have left and right frame red, painted as red, so identities. So if you think of identities as edges that can be collapsed to a point, then you collapse red edges to a point and you do get a proper globular diagram, right? And so um, the collection of globular squares in a double category C that will be a bicategory, which we'll write as HC, and we'll call that the horizontal bicategory of the double category. So this will be HC, the horizontal bicategory of a double category. You can think, if you're inclined to think about double categories first as bicategories, as double categories where every square is globular in this form. So this has a very nice categorical um, formulation. There is the vertically trivial embedding from bicategories to double categories. And so you can think of bicategories as being these double categories. All right. So now we want to consider relations between bicategories and double categories. So this will be in the framework of these things that I call decorated by categories. So this is the definition. So a decorated by category B, a decoration on a bicategory B is a category, B star, having the same collection of objects as B. So you have a B, a bicategory, then any category sharing the collection of objects with B, that will be a decoration of B. And we'll usually write them as B star. So if B star is a decoration of B, we'll say that the pair B star comma B is a decorated bicategory. So a decorated bicategory is just a bicategory together with a decoration. So if C is a double category, then we can associate to C a decorated bicategory. So the horizontal bicategory of C, that is a bicategory, and the category of objects, the category of vertical edges of C, that is a category sharing the objects of the horizontalization of C. So this pair here, C naught comma HC, is a decorated bicategory, which we'll denote as H star C, and we call this the decorated horizontalization of C. So the decorated horizontalization of a double category C is a decorated bicategory. Now, I will consider the following problem. So suppose I'm given a decorated bicategory, B star comma B, so bicategory, together with some extra collection of arrows sharing the same vertices. We want to find double categories C such that the decorated horizontalization of C is equal to B star comma B. So suppose you have a decorated bicategory. So you have a bicategory, a collection of vertical arrows. With that, I want to see how many or how I want to find examples of double categories having same collections of objects, same collections of globular two morphisms or two cells, same collection of vertical morphisms, but it being a double category. So we call these internalizations or lifts of decorated bicategories. So internalizations in the sense that decorated bicategories are enriched categories or enriched objects, and then we make them into internal objects, so decorated double categories. So a solution to a problem like this, to this problem for a decorated bicategory B star comma B will be called an internalization of B. So we're interested in the problem of existence of internalizations of decorated bicategories. So the problem of internalizing a bicategory to a double category through a decorations, which we think of an orthogonal direction in which we can lift our bicategory to a double category, can be interpreted as follows. So suppose you're given a bicategory, so a collection of globular squares of this form, and you're also given a collection of arrows sharing the same vertices as the globular squares. So, and we have that forms a category. And so what we want is, so if we have globular squares like this and we have vertical arrows, then we can just put these arrows here into all the holes that are left by the red edges, and we can form hollow squares of this form. So we can use the horizontal arrows and the vertical arrows to form hollow squares. So we want to find collections of solid squares, so fillers of those squares, which I draw here as blue or green, forming a double category such that if you already filled out all those possible hollow squares that you had, then the globular squares that you're left with are the globular squares that you started with. So this is the problem of existence of internalization sort of geometrically. Now, there's several examples of this. This has been done with different names in the theory for a very long time. So for example, if B is a two category, then we can decorate B with its category of horizontal morphisms or one cells. So that would be a decorated bicategory. So if you've heard about the double category of quintets, the quintets construction, that would be an internalization of this decorated bicategory. There's also a bicategory of adjoint pairs. The objects are categories. The one cells are adjoint pairs. And two cells are natural transformations taking one adjoint pair to the other. We can decorate that with the category of categories and functors. And so there exists a double category, the double category of adjoint pairs of Kelly and Street. And that will be an internalization of this decorated bicategory of adjoint pairs. And the same thing goes for the bicategory of spans. We can decorate that with a category of sets, and there is a double category of spans that internalizes that. We can do the same thing for profunctors. The bicategory of profunctors, we can decorate that with a category of categories and functors. And there is a double category of profunctors, which people call the double category of categories, that internalizes this. And then also for bimodules. So we have a bicategory of bimodules. Objects are rings, morphisms are bimodules, and two morphisms are bimodule morphisms. We can decorate that with a category of rings and morphisms. And so there exists a double category of bimodules that internalizes this. Now, all these examples work very well, and we like them very much. And they would suggest that for every decorated bicategory, there should exist an internalization. Now, we don't actually know if all decorated by categories can be internalized. So this whole project started with this decorated by category that I was studying, the double category of Hilbert spaces, Hilbert by modules over binomial algebras. And so you would decorate that with the category of binomial algebras and whatever choice of morphisms that you would have. And you would think that that would internalize pretty quickly or pretty easily. And it turns out that that's a very difficult problem. And so in general, we don't know if this has a solution for every decorated by category. And it turns out that the problem is a lot more subtle than you would think. So in all of these examples, there is a natural choice of internalization. But in all these examples, we can find different internalizations, inequivalent internalizations. So uh, there is a second double category of adjoint pairs. There is a second double category of spans, and not just a second, but many other double categories of spans. So if you're coming at this problem from the point of view of bicategories, well, it turns out that there's no canonical choice of internalization, but you have many different choices. Okay, and so well, it turns out that if you're trying to study this problem of existence of internalization, so the problem has minimal solutions. So these minimal solutions are called globularly generated double categories. So the definition is the following. So a double category C is globularly generated if C is generated as a double category by its collections of by its collection of globular squares. So what this means is that if C is a globularly generated category, double category, if every square of C can be subdivided into um, horizontal identity squares and globular squares. So every square can be written as a vertical and horizontal composition of horizontal identity squares and globular squares. So in general, if you have a double category C, you can consider the sub-double category generated by globular squares and horizontal identities. So that will be a globularly generated double category. We'll call that gamma C as it's written here. And so we'll call that the globularly generated piece of C. So it turns out that that sub-double category, gamma C, the globularly generated piece of C, is both the maximal globularly generated sub-double category of C, and it is the minimal sub-double category of C that satisfies a certain universal property. The universal property is this one that I have here. So the decorated horizontalization of the double category C is equal to the decorated horizontalization of its globularly generated double category. And moreover, so it satisfies this condition. So it is also a solution to the problem of existence of internalizations for its decorated horizontalization. And moreover, it is minimal with respect to that condition. So if there exists another sub-double category of C, uh, that is also a solution to the problem of existence of internalizations for the decorated by category of C, then this sub-double category has to contain the globularly generated piece of C. So the globularly generated piece of C, which is defined through this very innocent condition, uh, is actually the minimal solution to the problem of existence of internalizations for the decorated by category of C inside C. So so the sort of global statement, global restatement of this is that globularly generated double categories are minimal solutions to the problem of internalization. And so another way of saying this is that a decorated by category B star comma B admits internalizations if and only if it admits globularly generated internalizations. And every internalization contains a globularly generated internalization canonically. So you can restate this in fancier categorical terms. So it turns out that the category or the two category of double categories is fibered over the sub two category of globularly generated double categories, and that fiber is that the vibration is constant along decorated horizontalization, and so that gives you a universal property for the globularly generated piece. But this is basically summarizing that property. And so if we're interested in this problem of existence of internalizations, we are interested in globularly generated double categories. So let me just stop here for a second and ask if there are any questions. If there are any, you're very welcome to unmute yourself and ask. Okay, if not, let's move on to length and equipments. So this theory of globularly generated double categories allows us to somewhat unexpectedly define invariance, numerical invariance on double categories. So this goes in two ways. Number one, every double category contains a globularly generated double category canonically, and globularly generated double categories are described in terms of a given set of generators. So we can associate a length of that describes the complexity of an expression of a square in a globularly generated double category in terms of this given set of generators that we have, and we take the sum of all those numbers, and then we get an invariant of the double category. All right, so the definition is as follows. So this length invariant that I'm about to define is a measure of complexity on globularly generated squares of a double category, where a square is globularly generated if it is a square in the globularly generated piece of the double category. All right, so you take the point of view that if you're in a double category, then you're really not interested in uh, the decorated horizontalization of the double category. You take the point of view that you already know that. And so globular squares and horizontal identity squares, those are the simplest possible squares that you can consider in your globularly generated double category. So you mark those with a zero and you call them squares of complexity zero or length zero. Now, squares of complexity one then would be squares that you can construct as a vertical composition of squares marked with zeros. They're not of length zero. And so we'll call those squares of length one. So squares is of length one in a double category if it can be written or subdivided into vertically into squares of length zero. So horizontal identities and globular squares. So those are squares of length one. Now, suppose you have two squares of length one, let's say phi and c, and suppose they're horizontally composable. It might be the case that you can find vertical subdivisions of phi MC that match, vertical subdivisions of phi MC into squares marked with a zero that match horizontally in the sense that you get matchings of squares of length zero in this way. So you can compose them horizontally and then compose the whole thing vertically. So the horizontal composition of squares of length zero is of length zero. And so by the Ekman-Hilton argument, if your composition looks like this, you can first compose every pair, horizontally composable pair of squares of length zero horizontally. You'll get a vertical composition of squares of length zero. And so your square, your composite square will be of length zero. In that case, the square, the composite, will be of length one. And if that happens for every pair of squares of length one, then we'll say that the double category C is of length one. So double category is of length one if um, every globularly generated square is of length one, or equivalently, if for every two horizontally composable squares of length one, you can rearrange decompositions of the two squares into squares of length zero in such a way that we get this sort of horizontal matching. Um, so it might also happen that for two horizontally composable squares of length one, phi and t, the horizontal composition does not match ever. So for any choice of subdivisions of the two squares, phi and t, the two subdivisions look like this. And then you can't do the trick that we did before using the Ekman-Hilton argument, and then you can't write this horizontal composition as a vertical composition of squares of length zero. And so we call these squares squares of length two or one plus one half. It depends on the paper, but length two, let's say. And so you can define length of squares inductively in this way. So if you have a square that you can write as a vertical composition of squares of length two, and it can't be reduced to a square of length two, you'll say that the square is of length three, and so on and so forth. right? And so that defines this sort of measure of complexity of how squares can be subdivided into globular and horizontal identity squares. So that defines this length invariant, length n on squares. So in general, if you have C a double category, then you define the length of C, or the vertical length, as the supremum of all lengths of all its squares, right? So you have a double category, then you look at all the globularly generated squares, all of those have a length, and you just compute the supremum of those, and that will give you the length of the double category. And so we have a bunch of examples of double categories in one of the previous slides. It turns out that all of these double categories are of length one. So you do the computation, and it turns out that you can rearrange vertical compositions of squares of length zero, so that given two horizontally composable squares, the vertical compositions into squares of length zero do match. Now, these were the first computations that I did. So there was the conjecture, or the question, if there were examples of squares of, or double categories of length greater than one. And it turns out that yes, and the construction is not that difficult. It's a bit ad hoc, but it's not difficult to construct double categories of squares of length n for every n. And so just taking the limit, you can consider double categories of infinite length. So length is not a trivial invariant, and it measures this complexity of composition. Um, Now, you might wonder, what is so special about these examples that makes them being of length one? Well, one thing to observe, if you know what an equipment is that all of these examples are equipments. And so the obvious question would be, oh, sorry, I don't know what I pressed. Oh no. Oh, I'm sorry. I have to go back to my files. I'm sorry. There you go. Well, you didn't have to see that, but okay, we're back. Okay. I'm sorry about that. Um, I pressed something that I shouldn't press. Okay, so the conjecture is that equipments are all of length one. So not just these examples. The special thing about these examples is that they are equipments, and equipments are of length one. So what are equipments? What are frame by categories? Equipments or frame by categories are the same thing. So an equipment, or frame by category, is a double category such that the left and right frame functor, so the functor that associates to every square, its left edge and its right edge, is a bifibration. So bifibration is a fibration that is also an out-fibration. Now, what that means is that if you have a double category that is a frame by category or an equipment, if you have a hollow niche of this form, so you have, oh, all right. So if you have a square like this, a hollow square FG alpha, then there exists a Cartesian filler, so which we write like this, part of the filler, so you can fill it with an upper horizontal arrow, which you write as F star alpha G star, and you think of this as a way of pulling back the arrow alpha along the arrows F and G. And so these squares are special in the sense that if you get a square of this form, if you get a square of phi, where the vertical edges are composites, say F followed by H and G followed by K, then you can factor this uniquely in terms of Cartesian squares. So this factors uniquely as a vertical composition first of the Cartesian filler of the niche F alpha G, and then some other square completing the composition. And so the important thing about this is that in the case of squares like this, so suppose you have a general square phi with left and right edges F and G, then you can write F and G as F followed by an identity and G followed by an identity. And so the Cartesian condition would say that this square factors uniqually as a Cartesian square in the niche F alpha G, followed by a globular square. So in a frame bicategory, every square has the shape or can be written as a Cartesian square followed by a globular square. So this is why we say that in a frame bicategory, the shape of the two cells is in between squares and globes, because every square can be written as a very particular square, just a Cartesian square, and a globular square. Now, there are a couple of things about equipments that are worth saying and that makes them very liked and very popular. So the condition of this Cartesian condition, what it gives us is a restriction in an operation of scalars along vertical arrows. If you've ever done this in algebra or homology or cohomology or whatever, a change of base, formally what this process that I just described, where you have sort of a lower niche and then you complete it to an upper niche, then you think of the passage from the lower edge to the upper edge as a restriction of scalars. And so you would have the equal, so you have the other operation, the up Cartesian operation that would give you an upper niche, and then that will pull it down to a lower niche, and then you would think that as an extension of scalars. Now, also, this makes frame bicategories or equipments the preferred two-dimensional categorical structure for doing synthetic or formal category theory. Well, not just frame bicategories or equipments, but actually virtual equipments, but equipments. Now, the reason why I got interested in frame bicategories was that they're the natural way of defining two-dimensional symmetric monadal structures on bicategories in some cases. So it turns out that defining asymmetric monadal bicategory is a difficult thing, as you probably already know, but defining a symmetric monadal structure on a frame bicategory is not that difficult. And symmetric monadal structures and frame bicategories descend to symmetric monadal structures on their horizontalization. So if you have a bicategory and you want to make it into a symmetric monadal category, one of the possible strategies that you can follow is you internalize that into a frame bicategory, make that into a symmetric monadal structure, and then lo and behold, your bicategory is now a symmetric monadal bicategory, and you only had to check way easier axioms. So this is sort of the interest that a lot of people have, or one of the interests in frame bicategories. All right, so our conjecture is that if C is a frame bicategory, then the length of C is equal to 1. Now, if you follow this idea that extending or internalizing a bicategory into a frame bicategory is a useful thing, then you are into this business of internalizing bicategories into frame bicategories. And so if all frame bicategories we know are of length 1, well, we get a smaller set of possible internalizations of a decorated bicategory into a frame bicategory. And not just that, but length 1 double categories are way easier to describe than length greater than 1 double categories. Or at least they're globularly generated pieces. So these are just the squares or just vertical compositions of horizontal identities and globularly generated squares. And also, it might be the case that you want to do this, but you're not sure if a frame bicategory internalizing your bicategory exists. And one way of checking this is to decide if there doesn't exist an internalization of length 1 of your decorated bicategory. Then if this conjecture is true, then you know that there doesn't exist a frame bicategory internalization of your decorated bicategory, which is somewhat very abstract and but also can be very useful. So, all right, we want to solve this conjecture. So I'll stop here again and ask if there are any questions. Okay, if not, I can continue. All right, so now, so we want to solve this conjecture that the length of a frame bicategory is always equal to 1. So one thing that we should do, well, let me just mention that in the examples of frame bicategories that we have, there are some similarities in the proofs. There is something in common that makes them be of length 1, but there's no pattern that we can just extrapolate from the proofs. There are some things, but not really something that we've been able to make into a formal argument for the proof that frame bicategories are of length one. So one of the ideas that I had was to try to construct other examples of length one globularly generated double categories or internalizations. And so try to construct these in general and see what was the structure that allowed for these constructions and what was the structure in these double categories. So just try to create a machinery that will give us examples of uh, internalizations of length one. And so um, if you want to reverse engineer a double category of length one, then you have to look at what the squares of length one in a double category look like. And so it turns out that they have a very particular shape. They admit a very particular type of decomposition. So this is the following lemma, so which says that in a double category C, every globularly generated square as this phi of length one can be written as a very particular vertical composition. So this symbol here, the little square with the line, that will be vertical composition operation. And so this will have two sort of extreme squares, phi with an upper arrow, phi with a lower arrow, and then we'll have an alternating composition of squares. So horizontal identities and these squares that I call phi I. And so these are best described geometrically. Just, yeah, so there's like two special squares at the extremes of the decomposition, and then there is an alternating composition in the middle. Now, the extreme squares, the squares at the rightmost part of the composition and the leftmost part of the composition, look like these. So phi upper arrow will be a globular square where every edge is red except the upper part of the square. And phi down arrow will be a globular square where every edge will be an identity except for the bottom edge. And so we call these the top bond and the bottom bond of this length one decomposition. So you want to think of this as a hamburger or as a sandwich or something uh, for decomposition for a length one square. So you have your top bond, which is phi upper arrow, and your bottom bond, which is phi lower arrow. Top bond and bottom bond are globular in the sense. And then in the middle, you get an alternating composition of uh, let's say patties, meat, which would be the horizontal identities, and then cheese, which would be the squares CI, which are red boundary squares. Okay, so the um, so summarizing, the lemma says that in every double category, a length one square can be written down as a sandwich with an upper bond, phi upper arrow, globular square of the form that we have there, a lower bond called phi down arrow, a globular square of this particular font uh, shape, and then a middle composition, which is an alternating composition of horizontal identity squares and red boundary squares, which is the meat and the cheese of the burger. So we have a several story burger decomposition where you have a bunch of patties in the middle, top bond and bottom bond, and then you would have cheese in the middle. Um, yeah, so, okay, well, so all squares of length one look like this. Now, the question was, what is the simplest possible expression of this form that is not trivial? So if your square is of length one and is not globular, then it should have left and right black edges, not red. And so it should, the filler here should be non-trivial. What is the uh, easiest or most simple possible non-trivial filler here? Well, that would be a horizontal identity. So the simplest possible form of these several story hamburger decompositions for our squares of length one is like this. So you just get a top bond, bottom bond, and meat and no cheese. Um, and so we consider squares of length one in general double categories that admit decompositions like this. We call these canonical squares. Not every square of length one in a double category is a canonical square. In general, the filler of the inside of this sandwich or burger decomposition has several stories. But if you have a canonical square, then it's just top bond, bottom bond, and meet in the middle. So we want to consider canonical squares, and we want to see what's up with them. So it turns out that these are very nice squares in the following sense. So we have the following lemma. So if C is a double category, and we assume that every non-globular square of C of length 1 admits a canonical decomposition, then the length of the double category will be equal to 1. Remember, this is what we want. We want conditions that will tell us this double category has length 1. And so it turns out that if every length 1 square is canonical, then the double category will be of length 1. And the argument is extremely easy. So remember that all we need for a double category to be of length 1 is that the horizontal composition of squares of length 1 is again of length 1. Suppose you have two squares of length 1, phi and psi. Well, we know that we can write these in canonical form, top bond, bottom bond, and meet. So in this form. So just compose them horizontally, and then you get a composition like this. We can do the Ekman-Helton argument and then compose the top bonds horizontally, the meet horizontally, and the bottom bonds horizontally. And then, well, the top bonds will give us a top bond, composition of bottom bonds will give you a bottom bond, and the composition of patties will give you a patty. So the horizontal composition of horizontal identities is a horizontal identity. So we get that this is a square, a canonical square. So another way of saying this is that canonical squares in a double category are always closed on their horizontal composition. And so if all the length 1 squares in a double category are canonical, then the double category is of length 1. And so, okay, this is pretty good. We want double categories of length 1. And so if we want to prove that a given double category is of length 1, then we might just want to prove that every square is canonical. And so, okay, well, again, we want to construct double categories or internalizations of length 1, and we want to see what makes, how can reverse engineer now this condition of every square being canonical. And so, yeah, in this decomposition that I mentioned before, in this Berger decomposition, again, in the middle, you would have an alternating composition of horizontal identity squares and red boundary squares. So if we could turn that into just a horizontal identity and a red boundary square, then we would have a canonical square. So put another way, so if we had a method or a structure that would allow us, given a square of this form, so a red boundary square at the top, and then vertically composed with a horizontal identity, exchange a square like this, a vertical composition like this, for a square of this form, now the horizontal identity at the top, now exchanging the red boundary square that we had at the top with another red boundary square at the bottom, then we might be able to turn every square of length 1 into a canonical square. So this operation would be an operation of sliding red boundary squares down horizontal identity squares. So if we could do this, then we would have this hamburger decomposition. In the middle, we have this alternating composition of horizontal identity squares and red boundary squares. Then we slide down every red boundary square, down every horizontal identity square. And then if we do that, we would get a square like this. So we'd get a top bond, we would get a vertical composition of identity squares, which is an identity square. Then we'd have like all the compositions of red boundary squares that we would get sliding down all the horizontal identity squares. So we'd get a red boundary square, which is theta here, we get the bottom bond. But the composition of the bottom bond square and the red boundary square theta here would be a bottom bond square. So we would get a canonical decomposition for our square. So we have this operation of sliding red boundary squares down horizontal identity squares. Then the argument here is that every square of length 1 will be canonical. And then our double category will be of length 1, and then we will win. So yeah, so the type of structure that allows us to do this is this thing that I call pi2 indexing. So all of this has an up version, so we can also try to slide red boundary squares up horizontal identities, and then what we'll get then, the structure that will allow us to do that is called pi2 up indexing. But yeah, so we want some sort of structure that will tell us, okay, if whatever, you get a double category, and then you have a red boundary square composed with a horizontal identity square, then you can slide the red boundary square down the horizontal identity square, and then you'll get that every square of length one will be canonical. And so this pi2 indexing thing is the following. So suppose you have B star comma B, a decorated two category, or a decorated by category actually. So pi2 indexing on B star comma B is a functor phi from B star, the declaration of your decorated by category, into the category of commutative monoids, such that for every object in the decorated by category in the declaration B star, the monoid associated to the object is the commutative monoid of red boundary squares uh, in the by category on that object. And so pi2 indexing is just a way to make that correspondence into a functor. So it basically gives you a pairing between a morphism, let's say a vertical edge from A to B, and a red boundary square on A that will give you another red boundary square now on B. And this is the operation of sliding down. Now, the up version of that will be a pi2 of indexing. So pi2 indexing is just a functor from B star to commutative monoids. And this is defined for a decorated by category. So also defined for a double category. So an example would be this. So if you have A, an abelian group, and G, a general group, then you can consider G as a groupoid with a single object, and you can consider A as a two groupoid with a single object and a single one cell. And so you would get this would be 2 omega A and omega G. And so this would be a decorated by category. Then a pi2 indexing on this decorated by category turns out to be the same thing as an action by automorphisms of the group G on A. And so pi2 of indexing on this decorated by category is actually an action by automorphisms of G of the opposite group of G on A. And so you can see this um, just by writing down the definition. So yeah, not going to go into too much detail because I don't have a lot of time. So we have the following theorem, um, which says that if we have a pi2 indexing on a decorated by category, then to that we can associate a length one internalization, and not just a length one internalization, but an internalization where every length one square admits a canonical decomposition. So the theorem is if B star comma B is a decorated two category, then for every pi2 indexing phi on the decorated by category B star comma B, there exists an internalization called the cross product in the title of the talk, B cross phi B star um, of the decorated by category B star comma B, such that this cross product double category is of length one. And as I said, moreover, every square is canonical. So here, the idea of this is that we're reverse engineering this condition that I mentioned before, where if you could slide squares down horizontal identities, then you would get a double category of length one, or every square would be canonical. Here, we're sort of, yeah, again, reverse engineering that. So if we have a decorated by category, B star comma B, we have globular squares, horizontal identity squares, so we can build canonical squares. And so we just have to make this into a double category. The horizontal composition of squares like this is obvious. So you just sort of hammer in the Ekman-Hilton argument. And so that will give you horizontal compositions of squares like this. And so the difficult part would be the vertical composition. So vertical compositions here are a bit long to write down, but basically you have two squares like this stacked one on top of the other. So you would have a top bond, a bottom bond, and in the middle, you would have a horizontal identity, a vertical composition of a bottom bond, top bond. And so that will be your red boundary square and a horizontal identity. And then you slide down the vertical composition of the top bond and bottom bond, so red boundary square, down the horizontal identity. And so that will give you a canonical square, and that will give you a vertical composition. Now, there is a subtlety to this definition, which I might skip, but there is a hidden relation that it turned out to be very important later on in this double category that will tell you when two uh, squares of length one in canonical form are equal. And so, well, this kind of looks like this. So you have two squares, let's say the leftmost square and the rightmost square. These two will be equal if there exists a red boundary square nu satisfying that the top bond of the leftmost square is equal to the composition top bond in the second square. So that if we have a pi2 indexing, if we can slide down squares, down identity, horizontal identity arrows, this will be this composition. And then if these two squares are to be the same, then the vertical composition in the second to last square, the bottom part will be the bottom bond of the rightmost square. So here, the um, bottom arrows of this leftmost and rightmost square should be black. They're not red. So that's a typo, I'm sorry. Okay, so this double category is yeah, it's interesting because it gives us a method for constructing internalizations of length one. Their structure is as easy as we can get, as we mentioned before. So every square of length one is canonical, and so this is defined through this structure of a pi2 indexing. Okay, so in this example that I mentioned before, so if you have G group and A and B link group, then you would get a decorated by category formed by the double D-looping of A decorated by the D-looping of G. And as we mentioned before, and a pi2 indexing on that will be an action of G on A by automorphisms. And so you might wonder what the cross product of omega 2 omega A by omega G with respect to this action is. So it turns out that every square looks like this. So every square, you can write it down as an element of A uh, filling out a square with left and right edges decorated by G. And so the composition there tells you that the vertical category, the category of squares under vertical composition, is actually the D-looping of the semi-direct product of A by G with respect to this action. And so a better name for this construction would be maybe be the semi-direct product of B by B star with respect to the pi2 indexing, but I chose this name. So yeah, so I'll just stop here to see if there are any questions on this.
Can I ask one question? So,
Sure.
this concept you introduced length, and you talked about length one categories. So, the
Mhm.
theory also exists for length two categories and so on, or it is too difficult. Those canonical decompositions do exist for length two case.
No, so canonical decompositions don't exist in length two double categories. So, or not that I know of. I mean, you could, okay, not in this sense. They might exist um, in a different sense, but yeah, I don't know. That it might not be too difficult. I just haven't explored that idea. But that's a very good question. Thank you. So,
Thank you.
I mean, the decompositions would be decompositions into squares of length one, of course, right? And so you might wonder if there's a simplest possible expression for vertical compositions of squares of length one, and then you might want to study those decompositions. And so, yeah, that's a very interesting problem that I haven't thought about. Are there any other questions? Okay, then I'll move on to the final part of the talk. So, all right, so now, okay, we have this method for constructing length one internalizations of a decorated by category if we assume the existence of this structure pi2 indexing. Now, what can we do with this? So again, we're trying to solve this conjecture that that frame by categories are of length one. We could solve this conjecture for a special type of double categories for frame by categories. These are fully faithful and absolutely dense double categories. So I'll just define this. So suppose C is a frame by category. Suppose F is a vertical arrow, then we'll say that F is fully faithful if the horizontal identity on F is Cartesian. If the horizontal identity on F is off Cartesian, then we'll say that F is absolutely dense. So a double category, a frame by category, will say it's fully faithful if every vertical edge is fully faithful, and we'll say it's absolutely dense if every vertical edge is absolutely dense. Okay, so in a fully faithful frame by category, we would get for every square that looks like this. Um, so we have a composite vertical sort of left and right frame of our square phi, then that should be able, we should be able to factor a square like this into another square C followed by the horizontal identity on F. This is the same condition as being framed by category, just the only difference is that Cartesian squares now are horizontal identities. In particular, we can do this globularly. So if we have a square that looks like this, so left and right edges are F, then this admits a unique decomposition as a top bond square. So a globular square C followed by a horizontal identity square. And so you can see here how this type of condition would be useful if we're studying canonical squares. We have a bunch of examples, so I'll just go, I won't go into a lot of length in these. So in profunctors, our most important example, a functor. So remember, profunctors is the double category of categories, functors, profunctors, and natural transformations. So vertical arrows are functors. So a functor is fully faithful in the double category of profunctors if and only if it is a fully faithful functor, and it's absolutely dense if and only if it is an absolutely dense functor. So it's surjective on objects. And so we have similar characterizations for fully faithful and absolutely dense vertical arrows in a lot of the frame by categories that we know. None of these are fully faithful nor absolutely dense, but it turns out that we can extract a fully faithful and an absolutely dense double category from a frame by category universally, and that's very useful. And so, well, I'll just move on quickly because I only have 3 minutes, but it turns out that for every fully faithful double category, we can extract a pi2 indexing in this way. So a pi2 indexing essentially is a pairing between a vertical morphism and a red boundary square. So if we have a vertical morphism F and a red boundary square phi that match in this way, then we get, sorry, a pi2 up indexing, then the corresponding red boundary square would be the red boundary square that is given to us by the Cartesian decomposition that we get from the fully faithfulness of the morphism F. And so it turns out that, yeah, so we get a pi2 up indexing for every fully faithful double category. And so our main theorem is the following. So suppose C is a fully faithful frame by category, then there exists a unique strict double functor Q from the cross product of the category of objects, well, the decorated horizontalization of C with respect to this pi2 appendixing that we can extract from our fully faithful double category into the globularly generated piece of C, such that this double functor satisfies two conditions. Its horizontal, its decorated horizontalization is equal to the identity. So this functor is the identity on globular squares and horizontal identity squares, and it is surjective on all squares. So we can put this in terms of a category. So you can consider the category of frame by categories that induce a given pi2 appendixing. And so what this says is that the cross product is initial in that category. And that's a very nice statement, but essentially what it says is that if you have C, a double category that is fully faithful, then it induces a pi2 appendixing, and it turns out that its globularly generated double category can be written down as a double quotient of this cross product construction of its decorated horizontalization with respect to the appendixing you extracted. And so what this gives us is that if you have a double functor between double categories that is surjective on squares, then the length of the um, double category that you're covering is less than or equal to the length of the original double category. And so we know that cross products are of length one. And so what we get is that if C, so we get this corollary, if C is a fully faithful double category, then it will be of length one, which is great. This is our conjecture for fully faithful and, well, now absolutely dense double categories. Um, Now, a very important subtlety is this functor here, this initial functor, is not always a double isomorphism. So when I first wrote it down, I thought it was an obvious double isomorphism, but it turns out that it's not, and there's a lot of room there for exploration with this functor. And the example is very easy. And so just to end, this is bibliography. So this project has been going on for a bit of a while. So what is it, fourth paper, I wrote that with my student, Ruben Maldonado. And so that has already appeared in applied categorical structures. And then this fourth paper will appear in higher structures soon. So if you're interested in all in this, you can find the papers, and I would always be very happy to talk about it. And so that's it. Thank you very much.
Thank you, Juan. So,
Yes, thank
any
you.
questions or comments? So
Mm.
maybe I will ask one thing about this length again. Does this length behave really like length? So, for example, if we take two different those higher categories where we attach length, and if we apply some linear algebraic operation, the resulting will be the sum of lengths or whatever. Do we have such things?
Not yet. So I've always conjectured that the length is additive with respect to the gray tensor product of double categories.
Oh,
I think that is true. So that would be additivity. Um, so we have this result that if you cover a double category with another, then the length of the original, the covering double category, is greater than or equal to the length of the second, the covered double category. But that's it so far. So this length, yeah, I suspect that it does behave like a proper invariant. So I would call this sort of invariance properties. And so I think it is true that it behaves that well, but I don't know. So that's something to be explored. Another uh, thing that I wanted to explore about this length is if you have experience with this categorifications of invariants. So, for example, Kavanagh homology or Hegardt-Floer homology or things like that, that categorify polynomials and the Euler characteristic and so on and so forth. I think this looks a lot like some sort of Euler characteristic of some homology, and it looks very homology E when you define the length. So you're sort of considering compositions, and then there's this sort of measure of failure of something, and then or maybe not Euler characteristic, but the length of a given homology that you can associate to a globularly generated double category or something like that. That's another question somewhat related to your question.
thank you.
But this is
Yeah,
pretty unexplored and so I think interesting. But
yeah,
yeah,
yeah. It's very interesting actually. Because there are those, I also saw some papers on Euler characteristics of categories and so on.
mhm.
Uh, there should be some very deep theory, unexplored
Yeah.
territories.
Yeah,
So,
so the
yeah,
one of the first people I talked about this with was Bob Perret, so a very good friend. And he mentioned that he was always on the lookout for numerical invariants for double categories. That was one of the things that he always dreamed of, having sort of numbers associated to double categories that were like, yeah, like invariants like the Euler characteristic or some quantum invariant or something like that. Um, and so you can do this in some sense if you do like the classifying space of the double category and so on and so forth. But these are some more topological invariants. But this length invariant is more algebraic. You would always expect this topological invariance to have some relation to the algebraic invariant, but the algebraic invariant should say something about the algebraic structure of your double category. I don't know. Well, it's an interesting problem.
Any more questions or comments? Okay, so let's think one once more. And this is a very nice picture of Ankara.
Yeah. Yeah, it's a beautiful city for what I can tell.
Yeah, it is. So we will meet 2 weeks from now. So this time we will meet on Tuesday as usual. So hope to see all of you. So I'm now stopping the recording.